As I mentioned, the next speaker is Dr. Leslie SCHRADIN. He's a principal machine learning engineer at Qeexo, where he co-leads Qeexo's ML team to develop novel machine learning platforms and application, including Qeexo AutoML, FingerSense, and EarSense, deploying them to hundreds of millions of devices worldwide. Dr. SCHRADIN's area of expertise include machine learning, software design, and physics, and he holds a BS in physics from Yale University and a PhD in high-energy theoretical physics from the Ohio State University. Today, Dr. SCHRADIN will talk to us about tree ensemble model compression for embedded machine learning applications, and the floor is yours. Take it away.
Thank you very much, Ofer. Right. So just a quick overview. So I'll be talking about tree ensemble model compression. So why this kind of compression for embedded targets? One way we can compress these models is by quantizing them, and that'll be the primary compression that I'll talk about today. I'll go through some pros and cons for quantization and an example of how to do this and apply it to a big model, and finally wrap it up. Okay, so first of all, why compress tree ensembles for embedded targets? Basically, size matters, as we all know, for embedded targets. They're constrained by compute, power, memory, and therefore small models are desirable. And so then the follow-on question, why tree ensembles? Performance-wise, we at Qeexo have found that tree ensembles are often the best ML model type available when the models must be really small. Compression. Why compression? This is obvious. Obviously, when we compress the models, they're smaller. So, tree model quantization. I first want to just discuss what I mean by quantization. In this case, quantization is changing the data types used for the encoding for the model parameters from larger data types to smaller ones. While we do it, keep the behavior of the model the same as much as possible, it is impossible to make the model exactly the same, because when we quantize, we necessarily round some of the values inside the model, and therefore the quantized model is a little different from the original one. Finally, dequantization of the model of some of the parameters is sometimes necessary during inference. So for trees, the bulk of the data that represents the model can be categorized into these three sort of broad areas. First of all, we've got values at the leaves of the trees, so I'll call these the leaf values. There are also the feature threshold values at each of the branch nodes. And finally, the other data that's in there is the data that encodes the tree structure. So basically which nodes connect to which in the tree. These two, the leaf values and the feature thresholds, we at Qeexo have created implementations for quantization, and these are the ones that seem the most appropriate to try. So these are the ones that we can do. All right, pros and cons for quantization. The main gain is the obvious one. The quantized model is smaller, so we get the model compression from quantization. The main cost is the loss of model fidelity. So I've already said the rounding step in the quantization introduces some noise, basically, into the model parameters. And this noise causes the quantized model to behave a little differently from the original one. This difference is often small, but if it needs to be made smaller, that can be done by trading away some of the gains in compression. Okay, there is an extra point though on the gain side. For some of the ways that we can quantize the trees, and for some tree implementations, we need to save some extra data with the model that we didn't need before. And that data represents the quantization transformation information. So the main thing is that sometimes we need to dequantize some of the values on the device so that the model can behave as we want it to. Storing the transform cost bytes, which then eats into the gains. And the number of parameters and the bytes that they require can depend a lot on how we do the quantization. Okay, so an example. For this example, this is one of our sort of benchmark data sets that we use at Qeexo, which we call the letter gesture problem. This was collected on the Nano 33 BLE Sense platform while held in the hand using accelerometer and gyroscope sensors. While it's held in the hand, we traced out in the air letter gestures, A, O, S, and V. And then also while it's held in the hand, collected data at the same time where there's no gesture at all. So a 5-class problem. For the example I'll talk about here, I trained an sklearn GBM with default parameters mostly. So using that trained model, I want to talk about an example for leaf quantization. This is a representation of the very first tree in that model. And this is visualized by sklearn's plot tree. This very first tree is a binary tree, so it's differentiating one of the classes from all the rest. And you can see that we've got these split points. These are the branch nodes going down. And then the terminal nodes are the leaf nodes here. For this example, I want to just concentrate on the leaves. So there are 7 of these here. And want to say quantize these guys as though these are all the leaves in the model. Now, I'm listed out the leaf values down here at the bottom. You can see that these correspond to the values in the boxes. And these are what I've referred to as the leaf values before. So a possible way to quantize these would be just a simple affine transformation where, so I'll assume that we're going to do that quantization here and that we're going to start with float 32 and go down to uint8. So 4-byte floats down to 1-byte integers. The quantization is rather simple. Basically, what we're going to do is take the minimum leaf value, which is this minus 9.94, and map it to 0. Take the max one, which is 5.3, map it to the max value of our new data range, which is 255, and then scale everything else in between linearly. So we apply that transform, we get these leaves at the bottom, and you can see this guy's gone to 0. This one has gone to the max. And finally, we have to represent these in uint8, so they have to be integers. And we apply the rounding step. And this is where we lose some information in the model, but we've gained in bytes. Okay. For the sort of final part of the example, I'm going to take the whole model that we trained. And this one happened to have this kind of parameter set. With the 3 areas of bytes for the model, we've got the leaves, the feature thresholds, and then the node structure. In this case, I had about 3,000 splits and about 3,600 leaves. And with float 32 encoding, it's this many bytes in each. And it's about 1/3 in each, going up to about 40,000 bytes. So if we apply leaf quantization, what we can do is take all of the leaves together and quantize them all at once. So we can take them all down from float 32 to uint8, and we get about 10,000 bytes or a little more, reducing our model by about 27%. We do have to keep around the leaf quantization transform, or at least piece of it, in order to get probabilities out of the model. Basically, we have to dequantize the scores before we softmax. Otherwise, we won't get the right probabilities. Fortunately, because we can use one transform for all the leaves, we only have to keep one transform at the end, and it turns out we can keep just half of it. We only need to scale at the end. So this is very low cost in terms of the dequantization. If we wanted to do feature thresholds as well, same kind of thing. We go down to 3,000 bytes-ish for the feature thresholds. So we gain like 12,000 or 9,000 bytes. And our model is about half as big as it was. However, the cost in terms of the transforms necessary is a lot higher for the feature thresholds. Basically, for every feature used in the model, in this case, there were 735, we have to dequantize them on the fly in order to compare with the features on the device, in order for the model to operate. So for the features, we give back almost 6,000 bytes, still can reduce the model by 36% overall. Okay. Summary, tree ensembles, good for embedded targets because these small models tend to perform pretty well. And for embedded devices, the smaller, the better. For tree ensembles, the quantization types, we could do leads and or feature thresholds. The gains, model smaller. The cost is model fidelity. Okay. And Qeexo has product AutoML that does tinyML solutions automated for edge using sensor data. If you'd like to learn more, www.qeexo.com or email info@qeexo.com.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung, these three are the executive sponsors. And then followed by platinum sponsors, ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H-Impulse, EMSA Visual Sense, General Matter Labs, Green Waves Technologies, Hymex, Imagimob, Latent AI, Maxim Integrated, Qeexo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and SynSense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.